sharing on. Okay, questions. I'm in a different room today. Jenny.
Good morning. Can you please go over chapter 14, additional problem number 8?
Chapter 14, additional problem 8. Okay, let's see. The hammer, the 7.27, there's a round number. And I imagine that it was something else when it was a, well, actually, let's just see. Um, 7.27 times 2.2 equals. Yeah, that was a 16-pound hammer, obviously, originally. When you get some weird thing like this book was originally written in British units. We have the international piece. So I'm going to I am going to put on the whiteboard and share it so we can do this. Remember, folks, that once we get going here, if you have a question about whatever I'm sharing, make sure that you unmute and just ask me the question, because once I get sharing, I don't really see the chat anymore. Okay, so organized here because that doesn't work very well for sharing, and you can see my roof. So a 7.27 kilogram hammer on a 1 meter wire is released with a linear velocity of 28 meters per second. What reaction force is exerted on the thrower by the hammer at the instant before release? This is a basically a both centripetal force question, which also means you need to understand radial acceleration. As I said way back in the first week of class, which just seems like yesterday, to be honest, there are things that we will learn early on that we'll come back to, we'll still be coming back to at the end. And here's an example where radial acceleration gets brought in. So here we go. We have, and this is not a proper free body diagram per se, I'm just going to sketch out what's going on. We have a person who, and we're looking down on them, and they are spinning around with a hammer. And that, go and look up hammer throw if you haven't seen, it's a sport, and they're spinning it around. And they accelerate as they spin around until they reach the fastest point, and as they spin around, they come out and let it go. So let's say they let it go, and then as soon as they let it go, it goes straight, right? Because the person is giving that radial acceleration, and the radial acceleration is only to change the direction. Once they let it goes straight. And we again have that piece of the centripetal force is the force the person puts onto the hammer to change its direction. If you really want to understand centrifugal force, which is the one we often mistake for centripetal force, it's the force that the hammer puts on the person. So remember, equal and opposite. And this is asking you for the force exerted on the thrower by the hammer, which is just the same magnitude, but it's pointing, it would point in. So on the hammer, it would be a force going this way. On the person, it would be a force going the opposite way. So let's just see what we have here. Let's go with the centripetal force, which again, the force on the hammer by the person equals the mass times the radial acceleration, which equals 7.27 kilograms times, radial acceleration. Radial acceleration equals v squared over r. We have a 1 meter wire. So it's going to equal, at the point of release, the v squared, or the linear velocity, is 28 meters per second. That's all going to be squared, all divided by 1 meter. Once this is all done, we're going to have meter squared divided by second squared, and one of the meters will cancel, so we'll be left with meters per second squared. So essentially 28 squared, which is anybody good for 28 squared?
784.
All right, couple. 784 meters per second squared. 784 meters per second squared. So we multiply the 784 by 7.27.
You get about 5,700.
5,700.
5,700, okay. Which is probably why it goes with 5.7 kilonewtons, which would be 5,700 newtons. Good. So there you go. And which again is equal to 5.7 kilonewtons. Any questions on that one? That clear, Jenny?
Yes, I got it. Thank you.
Yeah, you're welcome. Okay. Next, any questions? Any areas? Yes, Amos.
Yeah, I understand the general concept about I think additional problem 9 about the banking on the racetrack.
Yeah.
It's hard for me to visualize it because I understand that you want to shift like their center of gravity in line with the horizontal component of the friction, as well as the elevation. So then you get like a pushing force instead of friction. But it's hard for me to just visualize it, if that makes sense.
Totally makes sense. Let me do it. It's a important one to understand. Let's share the whiteboard. Okay, so this is again chapter 14, additional problem 9. The one before was additional problem 8. Okay, so this is the old why do we bank a curve piece. So when we go around a corner, we need to lean in. Why do we need to lean in? We need to lean in so that actually the, well, let me just show that part first. So let's say we, somebody's going around a corner, and we look at them from the top. Let's put them on a bicycle because, hey, it's just easier. They're going around a corner. this way, which means there has to be a force pushing that way in order to make them go around the corner. That's a given. We need to have a force that way to go around the corner, or you don't go around the corner. So if we looked at the person, if we did a view that way so that we were actually looking at the person straight on, and yes, we know that drawing is not my forte. So somebody's on a bike and they are going to need to have a force that is that direction. And the only place you can get that force, the only place you can get that force is through friction in the tires. That is the source of that of this centripetal force. That's the only place we get it, right? And that's important to know because, you know, there's no magical force that suddenly is pushing on the side of you. Maybe if you're in a really windy crosswind, possibly you could get some, but in general, the only source of a force that's going to allow you to turn that corner is friction from that's pointing on the side. At the same time, we have another force that is up. So this is the frictional force, which has to equal the centripetal force. They have to be the same or else you slide. Just saying, if there's not enough friction to do it, you'll slide out. And if there's not enough centripetal force, you won't go around the corner. So and this is the normal force component of your ground reaction force. This is on flat ground. I'm showing the flat ground scenario right here. Of course, we have our XY theta reference frame, not that we need it right now. And we have gravity. So those are the three forces that are acting on this person. These two forces together, the frictional force and the normal force, go together to be the the total ground reaction force. So the total ground reaction force in this case looks something like this. So that's the ground reaction force. And it's just these two added together, right? Now, if you think about angular momentum or some element of rotational motion gets added to a system if the external forces outside of, you know, the center of gravity do not go pass through the center of gravity. So at this point, if you weren't leaning over, this would be the line of action of the ground reaction force, and clearly there's the moment arm for it. So you have a torque happening here. And so if this person was upright right now, they would essentially rotate off this way because there's this torque acting on them. Which is why you have to lean. So this person, in fact, shouldn't be like this. This person will look like, let me just erase this. Instead, this person is going to be looking like this. Okay, so they're leaning over so that the ground reaction force ends up going right through their center of gravity. And they don't, even though I know they're not right over top of it, because there's a torque this way, they don't tip over because of the forces, the way the forces are acting on them. There's a torque that prevents them from falling over. That's why you have to lean over. So you lean into the curve. Now, why do this part is all to do with the friction. So when I'm on flat ground, all of this centripetal force comes from friction. Ultimately, this ground reaction force is the same whether this total ground reaction force is going to be the same whether I'm on a banked curve or not. It's just where the source of the force is, how much of it comes from friction, and how much comes from the normal force being 90 degrees to the surface that we're looking at. So this is the flat ground. Now, no matter what, I need, so this in this flat ground, this is going to equal basically the vertical force. As soon as I have and because the centripetal force and the vertical push up force of the ground don't change. Their requirements don't change because I still need, even on a banked surface, I still need the same centripetal force to go around that curve. It's just, I'm changing how much of it comes from friction. So if I was to redraw that same person as much as I can, same angle, but the forces are still going to be, they're still going to have the weight force. And they're still going to have this same ground reaction force. It's going to be the same. Ground reaction force. But let's say instead of having like in this case, it was flat ground. In this case, it's curved, it's banked. And let's say it's banked at an angle like that. Now, the two components that are going to make up this ground reaction force, and the ground reaction force is still going to be the same, but it's now going to be made up of two reactions that look like here and look like here. And this is the force of friction, and this is the normal force. So in this case, over here on the flat ground, the force of friction and the centripetal force are the same, and the normal force and that vertical force that overcomes weight is the same. Over here, the force of friction and the centripetal force are not the same. You still have the same ground reaction force because the ground reaction force is made out of the vertical component and the centripetal component. So this ground reaction force is going to be the same. But now only a small part of it is made out of friction, and a larger part of it is made out of a normal force. And therefore, you're not relying on friction the same. Remember, friction has a limit. That static friction has a limit. And if the centripetal force that you need to make that turn is larger than the available static friction, you're going to slide. You don't want to slide. So by banking the curve, you make it so that same ground reaction force, meaning you have the same centripetal force and the same vertical force, but now only a small portion of it comes from friction and a much bigger portion of it comes from the normal force. Does that help?
Yeah, I just want to clarify because let's say if you're turning on a flat ground, your ground reaction force still has components of the normal force and the friction force. Is that correct?
Yes, but on the flat ground, the normal force equals the vertical force and the friction force equals the centripetal force. So if you're turning on flat ground, or not banked curve, but a flat, no matter what, we are talking about all at the same vertical level. So you're not going up or down a hill, but just the surface that you're on happens to be banked. And so when it's flat, when it's totally flat, the frictional component and the centripetal component are the same. Remember, centripetal is going in towards the center of the curve. If you're on flat ground, the only thing that can create that centripetal force is friction, which is here. Over here, you still need that same centripetal force, but it's now mostly created by the normal force, and very little of it is friction. But when it's flat, the normal force and the vertical force are the same, and the frictional force and the centripetal force are the same. So essentially, when you rotate, you are now making it so that, or when you bank the surface, the centripetal and the vertical still say the same, but the frictional and the normal rotate with the surface. I don't know if that made things more complicated, but the
only thing that the reason why you want the banked surface in the first place is because you're worried if the force of friction, like static friction, becomes less than the centrifugal force. Is that correct?
Yeah, if the force of static friction, of maximum static friction, becomes is less than the centripetal force that you need to go around that corner, your tires will slide out, or your feet will slide out, or mostly your tires will slide out on you, because there's just not enough force to create the centripetal force that you need, and your tires will slide out from underneath you. Now, think about it. When are you going to need larger centripetal forces? Well, typically we need larger, well, let's just remember what centripetal force, mass times radial acceleration, which is going to equal mass times velocity squared over r. So we need that a large centripetal force when the mass is bigger, when the velocity is bigger, and this is really, the velocity is the thing that we control the most, and of course, when r is smaller. The smaller r is, the tighter the turn. When we're looking at it from a linear perspective, the tighter the turn and the faster the velocity, the more radial acceleration we need, and the more likely we are, which means the greater the centripetal force is. So the faster we go around a curve, the more centripetal force we need, and therefore the more frictional force we need in order to create that centripetal force.
And the frictional force is only equal to the centripetal force in this flat scenario because you don't have the normal force that's really contributing to that how you say, the inward change of direction. Whereas in the curved, you have that normal force doing the large proportion of that inward curved direction. So you don't need as much force of friction, if that makes sense.
Well, and think about it. Yes, the normal force, this ground reaction force is being created more from a normal force than for the friction force. But no matter what, normal force is perpendicular. You know, if this is my surface, by definition, the normal force is 90 degrees to that surface, and frictional force is along that surface. That's just the definition of normal force and frictional force. And yes, by rotating it, more of the ground reaction force is created by the normal force, the 90 degrees, and less of it is being created. If you are on a perfectly banked, you know, if you really were on the absolute perfect bank for a particular situation, you could actually, if this was the direction of your ground reaction force, as I've shown here, and your my ground actually went like this, so that it was 90 degrees to that ground reaction force, in that particular case, everything would be created by normal force and nothing would be created by friction. It's, you know, that's like a instantaneous perfect banking, but it could happen.
Is that like theoretical or is that actually practical?
That's not theoretical. That can happen. If you think of a velodrome, have you ever been in and looked at a velodrome a little bit when you watched? You know what I'm talking about with a velodrome?
No, I'm sorry. I don't.
You don't know what a velodrome is. Okay, I'm sorry. That wasn't a. That's a sporting thing, not a not a. A velodrome is where they do the bike racing. And anyway, if you watch the Olympics, I like to watch the Olympics, they have a thing called the velodrome where they do bike racing. They now do some bike racing out in you know, fields and on roads and things, but they do bike racing in a velodrome, which is a round, big round stadium, and they go around, and there's a flat part at the bottom, and then it banks up and up and up and steeper and steeper. And so the faster they go, the higher up on the wall they're going to be, so that they can try and keep their wheel as 90 degrees to the surface as possible. Because so they can kind of choose where they're going around, so that they are as 90 when they're leaning in. As they speed up, they can kind of keep their tire 90 degrees to the wall that they're riding around. It's a good example of something where, and you can try and play with it to make sure that for the speed, you know, the faster you're going, the more centripetal force you need, and therefore the more you want to be on a bank against a bank surface so that your tire doesn't slide, because they certainly don't want their tire to slide in a race.
Also, I think in bobsleigh, they have on the truss, they have like slopes when it goes around the curve, right?
Absolutely, they do. As you go around a curve, you can see them as they go around a bobsled curve, that they ride up, and again, it's ice, so that you definitely don't have friction to do it. You are riding up so that you are on the side of that curve. So that it's all normal. So it's not theoretical at all. Well, I mean, it's theoretical and it's practical. Any other questions on this one? Does that make more sense, Amos?
Yeah, it clarifies a lot.
Good. Okay. Let's see what we have. Somebody asked about the grades. I think they've already been released. Hopefully you can see them. Next question.
I have a question about additional problem 1. So I know how to do it, but I couldn't get the results from the book. So is it?
Well, let's try on all of them or just one of them?
Yeah, just one of them. So because all
no,
of them
but,
just kind of.
So for all of them, you didn't get the same version that the book got?
Yeah, the same, like the same difference. So.
Well, the radius of, sorry folks. I have a dog. Dog is not happy right at this instant in time. Very cute dog, very happy dog in general, but I've got him in here and we've got some visitors into the house and he doesn't feel right. He's trying to protect me. So the radius of gyration of the thigh, that one, Elena? The radius of gyration of the thigh with respect to the transverse. Yes. Okay, let's just look at that one then. We're gonna share our whiteboard. So this is chapter 14, additional problem 1. The radius of gyration of the thigh with respect to the transverse axis at the hip is 54% of the segment length. The mass of the thigh is 10.5% of the total body mass, and the length of the thigh is 23.2% of the total body height. This is a typical, very typical analysis of how we get the moment of inertia of a body segment. So what is the moment of inertia of the thigh with respect to the hip for the males of the following body masses and heights? So let's go with A. A has a mass of 60 kilograms, height 1.6 meters, and the radius of gyration is with respect to segment length is 0.54 or 54%. And segment length with respect to total height is 0.2 0.232 or 23.2% of your thigh is 23%, just over 23% of your total height on average. Obviously, these are anthropometric, which means it's population data, which means not everybody's thigh is 23% of their total height, but on average, it is. And the mass over of the thigh is divided by the total body mass.
It's 6.3.
No. Well, the mass of the thigh is 6.3. Let's just put this equals 0.105 first. So let's get the mass of the thigh, and this is the radius of gyration of the thigh at the proximal end. That's not around the center of gravity, which is where it would be the smallest. It's not around the distal end, it's around the hip. So mass of the thigh is going to be 0.105 times 60. 6 point what?
6.3.
6.3. So that's 6.3 kilograms. And the segment length is going to equal 0.232 times 1.6 meters. Anybody have that one? Hopefully everybody's plugging it into their calculator.
0.3712.
37.
Yeah, actually I found my mistake. So.
Oh, good. Okay. Well, we'll finish it anyway. 0.3712, and then the radius of gyration of the thigh around the proximal end, which is the hip, which is going to be 0.54 times 0.0. Just out of, looks nicer. So point what?
0.2004.
2004. And that one's going to be meters. Again, that 20 centimeters, which is what this is not something that you can take a tape measure and go, this is where it would be, because radius of gyration has to do with how it's distributed around the hip, the thigh around the hip. And if you you would have to sort of allow it to swing so that you could calculate what that is. And so our moment of inertia is going to equal mass times radius of gyration squared, which is going to equal 6.3 kilograms times 0.2004 meters, all squared, which is
it's 0.25. Yes.
okay. There we go. Any questions on that one? Come here. It's okay. It's okay. Any questions?
No, I found my mistake. So I thought it's 5.4%, not 54%.
Ah, okay. There you go.
Yeah.
Okay. Now, it makes sense that it's 54 when you think about it, because the center of gravity of the sky is pretty much halfway. Sorry. Forget that. That's the radius of gyration. You don't really know what that is, so it could have been 5.4, but it isn't. It's 54. So we'll clear that canvas and stop the share. Oh, you want to see my dog? Okay, here's my dog.
Yeah.
There's my dog. Okay, Duff. This is Duffy. Oh, sorry, folks. There's my dog. You probably don't notice him, but every once in a while he does creep into the lectures down at the bottom. I redid all the lectures from last year, but we did it in a smaller space, and he was in a lot because he just wanted to be close. So anyway, there he is. That's my dog. Okay. Next question. Anybody have one? Wow. We're all good today. Again, any question at all? I just, I'm sure the exam schedule is out now. I want everybody to be aware that I will schedule a couple of tutorials before the exam, between when class ends and we have the exam. I think it's on the 23rd. And yes, Friday the 23rd. And make sure you know whether you're in section M or N, because I'm going to have to start the two exams at 2 different times. I think M starts at 9:05 and N starts at 9:10. That they are trying to not have everybody start in the whole university at exactly the same time. So, and I'm sure you've seen this in some other core courses. They're trying to take the bigger classes and have them start just a few minutes later. So again, they've split you up. And I mean, everybody will have the same amount of time and a full amount of time, but you'll just start that 5 minutes later from each other. So make sure you know whether you're in M or N before we get to the 23rd. Any other questions?
Yeah, I have a question. So you told you posted exams grades, so I just checked and they are not there.
I thought somebody said they did see it.
I could see my grade.
Yep.
I can see mine.
It's just not at the top. You have to go down and click.
It's in the middle. It's in the middle. I don't know why. It's in the middle. It's between some of the
oh, yeah.
See it? There. So
yeah.
I was sure.
I can see.
I actually got thrown by that myself because I thought I had made it visible, and I thought, oh, it's not there. And then, oh, it's in the middle there. It's between some of the lab grades. It must do it by, I don't know, timing released. Amos.
Yeah, I don't know if this is the appropriate time because I don't know if you've already started working on the exam. It's just the format, because we're given I think, is it over, was it 3 hours or two to 3 hours?
It won't be a full 3 hours. With the online exams, I didn't make it 3 hours last time because so I haven't totally, I will post what it will be. It will probably, there's a possibility it'll be in parts. So let's just wait and see. Okay, I will post. Parman.
Hi, Professor. I was just wondering if, similar to midterm 1, are we gonna have a chance to view our midterm 2 with a TA?
I will try and set that up. Yes.
Perfect. Thank you so much.
Can't happen until after the makeup people have written. So.
Yeah, for sure.
Kajoki.
For the final, could we maybe not have questions that are worth like 7 points? Because it's like, you get that question wrong, you're pretty much failing the thing at that point.
Well, you are or you're not. So I would have given you that exact same question in a, the reason we have those in there is because if we wrote a paper and pen, if you wrote a paper and pencil exam, my traditional paper and pencil exam is roughly 50% multiple choice and 50% problems. And the 50% problems are things where you have to draw the free body diagram, then you have to set up the equations of motion, and then you have to, or equilibrium often, and then you have to solve them, or you have to calculate the angular momentum and graph it or something like that. So those problems are worth usually 6 or 7 marks by the time you do that, and there's lots of part marks. It's not, okay, you got the final answer right, so you get all the marks, and if you don't get the final answer right, you get nothing. I don't do that. I get lots of part marks, and those questions that are worth like 5 or 6 marks are all ones where there's at least 5 answers that you give along the way. All of those answers are answers that you would have had to solve anyway. So now it's my way of giving you part marks for doing a problem straight through. And by doing it, you would have had to go through the steps of, so for example, the projectile motion question was worth like 5 marks in the first midterm. It was worth like 5 marks. And along the way, you had to find out what were the X and Y components of the velocity and how high did it go up. And those are all things you would have done on a test, and it would have been worth the same amount on a test. So that's my long answer for saying no. There's still going to be questions that are worth 5 or 6 marks because those would have been the steps you would have had to go through even if you did it on a paper. And those would have been the part marks you would have got even if you did it on paper.
Okay, could we maybe have some like throwaway questions, like some questions that are just like super easy, just, you know, to level out the playing field.
There were ones that people got. There are questions that, you know, you might not think about it, but they were not that hard, and most people got them.
Yeah, but I mean stuff like, what's the value of gravity? Or like, what do you have to have in a free body diagram? Like, stuff that relate to the class. But just like, make the test a little easier.
Well, I'll see how it goes. You know, I look at it this way. I know you don't look at it this way. Yes, I saw that, Perla. And some of those questions were easy. I know you don't think so at the time, but most people got them right, and there were ones like that. If it's too easy, you know, I might actually have to lower the grades, and you'd never want me to do that. So,
like it could even be like a bonus question at the end, like, you know, just like something.
Well, we'll see.
Can I add on to that and say, could we lessen the drop? What are those things called? The list. I don't know.
The takedown menus, like the multiple matching ones.
Yeah, because I get the concept, but it's just when you're super stressed and the options don't go away, you start to just pick the same ones and you don't realize until afterwards. I mean, if there was a way for E-class to maybe get rid of the options once you click them, that'd be really nice.
Yeah, if I had been able to do that, you're right. That would be nice. That would be nice, and I'm sorry it doesn't do that.
It's not your fault.
It was the only way I could come up with of having you do a problem and give you part marks for it. Other than, and I expect this to be on the final, other than for you to type it in. Okay, so you type in the acceleration, the let's say we were doing the centripetal force question that we did right at the beginning, question 8. And you would, I obviously couldn't get you to draw in free body diagrams or sketch. You're just going to have to do on your own. But you would have to do F equals mass times velocity squared divided by R, and then plug in everything and then give me an answer. If you just gave me the answer, I wouldn't, it's not enough information for, even on a exam, if somebody just throws in the answer, I don't give them full marks. They have to have something on that piece of paper that makes me know that they sat down and figured it out. So that's my way of doing it. And the alternate way is for you to type it into a box that would then be marked by the TAs.
Okay. Yeah. I get it. You guys probably have very limited options, especially with all this. But yeah, just thank you.
Even drawing a free body diagram, that's the one thing that I would love to have you guys do. And I know you might not love it, but it to me really shows that you see what's going on. And when you get out in the world, you sort of have to picture, especially if you're standing in front of a piece of fitness equipment or something like that, or you were putting you know, you were trying to manipulate something and you wanted to think about which direction you were putting those forces. Whether you do it by instinct or not, you are applying forces to do something, or the amount or the direction of the force in the piece of fitness equipment is going to govern which muscle group is active, which is pretty darn important if you are, you know, working on a fitness rehab or something like that. So that the best way I have of capturing that is a free body diagram. It's the one thing in all of the digital world that I cannot easily get you to do. There would always be a free body diagram in every paper and pencil second midterm and final exam that you would get in here, but I can't. All I can get you to do is to identify errors in free body diagrams that I would give you or something like that. Any other questions? Oh, we're a quiet group today.
I sent you links in chat for figure skating. So
I did get that. Thank you.
Welcome.
Thank you very much. Well, if nobody has anything more, I'm going to at least turn off the recording.